Hello and welcome to this massive open online course on JDK 8. In this course we're going to be looking at some of the new features that are being included in JDK 8 and the Java programming language and Java libraries, which will allow you to take a more functional approach when developing applications. This will use Lambda expressions and the Streams API. My name is Simon Ritter and I work for Oracle as a Java technology evangelist, and I'll be guiding you through the 3 weekly lessons that we have for this course. The aim of this course is to give you an idea about how you can use Lambda expressions. So we'll talk about the various aspects of those Lambda expressions in terms of the syntax, where you can use them, how you can use them, and so on. Then we'll talk about the Streams API and how they can use Lambda expressions extensively to give you a more functional style of programming using JDK 8. What this gives you, when you understand how to use these correctly, is a much better way of solving a lot of common problems in terms of how we process data, how we process collections of data. It gives you a much more concise, more flexible way of doing that, so the code becomes easier to read, easier to understand, and easier to maintain. One of the other big advantages of this is the fact that you can now much more easily take advantage of multiple core processors, and if your machine has multiple processors, then the parallel execution of code can be made much simpler using this type of syntax. Let's start with lesson 1, and in this lesson we're going to look at Lambda expressions. The agenda for this lesson is, firstly, we'll start talking about why we need to add Lambda expressions to Java. Java is 20 years old and we've been very happily programming for those last 20 years, or 19 years, since JDK 8 is about a year since it was released. So we've been using Java for a good 19 years without Lambda expressions. So why do we need to add them at this point in time? We need to understand the syntax of Lambda expressions, so we'll cover that in some detail. And then we'll look at places where you can actually use Lambda expressions. And this is essentially wherever you can use a functional interface. So we'll describe what functional interfaces are, their definition, how you use them, and so on. We'll move on from there to looking at some of the new functional interfaces that have been included in the java.util.function package. And these are very relevant when we start talking about streams in lesson 2, because they are used extensively in conjunction with streams. One of the other things that we've included in JDK 8 around Lambda expressions is a shorthand way of creating certain types of Lambda expressions, where you're using just calls to a particular method or you're using a constructor. So these are method and constructor references, and we'll explain the 3 different situations where you can use those, and again the syntax and the way that those work. There are some quite, not complicated rules, but there are some rules that you need to understand about how you can reference variables from the surrounding scope in a Lambda expression. And so we'll cover that in some detail. We'll talk about what the rules are, how you can use things, and also how the compiler can actually help you in certain situations. And then the last part of this lesson, we'll look at some of the new methods that have been added to the existing JDK 8 libraries outside of the Streams API, where you can use Lambda expressions, and some of the really useful things that you can do for collections and also for things like logging. We'll start then with part 1 of lesson 1, about why does Java need Lambda expressions. Now, I mentioned that what this allows you to do is to simplify how you can take advantage of multi-core processors and multiple processors. And if you look at the history of Java, what you'll find is that right from the very beginning, Java had the concept of being able to support multiple streams of execution, multiple threads of execution. In JDK 1.0, you had the java.lang.thread class, which allowed you to create a separate thread. You could define, through the use of something like a runnable, what the code was that you wanted to execute within that thread. And that was great because it meant that it was very simple to create multiple threads that could do things potentially in parallel. The problem that we had with that was when you had several threads, all of which wanted to work together. If they were working separately, that was no issue. But once you want threads to work together, to share data and to be able to coordinate their activities to a certain point in time, then you're quite restricted in what you can do with a thread. There are essentially 4 methods in the thread class that allow you to do that. So there's sleep, interrupt, wait, and notify. And writing code that has multiple threads working together just using those APIs is actually very difficult. And what we wanted to do was to simplify that. In JDK 5.0, we introduced the concurrency utilities. This was JSR 166, Java Specification Request 166. What this provided you with was quite a big toolbox of new classes and APIs that made this coordination of multiple threads simpler. We introduced the kind of concepts that people who'd done multi-threaded programming in other languages and other platforms were already used to. Things like a semaphore class, things like mutexes, read-write locks, atomic operations, all of those types of things that people were familiar with and could then use to create better code in terms of multi-threading. In JDK 6, we added a few more advanced features, things like phasers, which was just another way of having multiple threads all working simultaneously and then arriving at a particular point in time so that they could deliver a set of results. In JDK 7, we had another attempt at making life easier for writing multi-threaded code and code that ran in parallel. We introduced the fork join framework. And what this gives you is the ability to take a single task, which can be broken down into multiple subtasks, and have that happen recursively until you get to a small enough task that can be handled by a single thread. The framework takes care of creating a pool of threads to use. It takes care of allocating various tasks to the different queues associated with those threads, and then it takes care of gathering all the results together once the queues have been processed and delivering a final result. So that was good, but it still had the drawback that it required quite a lot of boilerplate code to use that effectively. For JDK 8, we sat down and we thought, well, we want to add more features. We want to make it easier still for people to write parallel code. And at this point, we realized that we couldn't just add more APIs and classes to the standard class libraries. In order to make life easier for developers, we had to make some changes to the language syntax that we could then use in conjunction with new APIs to make this simpler. And this is what the Lambda expression syntax, and Project Lambda as it was, is all about. So this is why we wanted to add lambdas. It's primarily to make life easier for you as developers to write parallel code that could work in a simple way. Let's have a look at a sample piece of code. And this is the kind of code that we write a lot in Java. What we have here is a collection of data. In this case, it's a collection of records about students who've taken exams over various years. What we want to extract from this information is what was the highest score that any student got who graduated in the year 2011. And we can see here that we've got a fairly simple piece of code. What I've done is I've got my collection of students, and then I've created a variable called highest score. And I've assigned that an initial value of 0 so that we can update that as we find higher scores. Then we use the very common way that we do things in Java, which is we iterate. Java is an imperative language, and that means that we have sequences of commands which can manipulate variables to update things and process data as we want it. In this case, we want to iterate over the collection of students, so we look at each student in turn, looking at their graduation year and looking at their score. So we use the more modern for each syntax for this loop, and this in itself hides some of the details, because in this case what we will actually have to do is to extract the iterator from the collection of students, and then we're going to have to repeatedly get elements from that iterator, so we actually move through the collection until there are no more elements left. So the syntax of that for statement is actually a little bit more complicated. We're just using a shorthand which simplifies it in terms of our code. As we move through the collection of students and we look at each record, we're going to compare the graduation year of that student to 2011. If they graduated in that year, which is the year we're interested in, then we look at their score and we compare the score of that student against our current highest score. If the student got a higher score than that number, then we assign the value of our highest score value that we're recording to whatever that student got in their exam. At the end of this, what we're going to have is the highest score that any student got in the year 2011. We solve the problem. There is absolutely nothing wrong functionally with what we're doing in this code. So the functionality works perfectly. The problem is in terms of how we would want to process that if we want to take advantage of multiple cores and multiple processors. By having our loop here, what we're doing is we're controlling iteration. So we're defining through our loop the order in which the elements of that collection are going to be processed. That means that we in effect have a contract between our code, the compiler, and the runtime that states the order that they will be processed in. And although it doesn't actually matter in this case, if we were doing other things which did require that order to be maintained, we couldn't break it up into parallel operations. Because by breaking it up into parallel operations, we would introduce non-deterministic behavior, because different threads could execute at different times, they could be looking at different pieces of data, and so we may not always get the same result. So we have control over the iteration, which means that our code is inherently serial. We start at the beginning of the collection, we move to the end of the collection. The other problem we have is even if we were to rewrite our loop and try and avoid using a loop explicitly, we still have a variable, highest score. And this is mutable state. We're having a variable that we can change, and if we were to have multiple threads, we would still have problems because it's not thread safe. Multiple threads could be updating that variable at the same time and overwrite the changes which are made by other threads. We would need to introduce locking to prevent multiple threads from accessing it at the same time, and that would add more work to our application code. So right now we have code that works, but it's not good in terms of multi-threading and parallel execution. Let's take the same code and rewrite it using a more functional approach. Now we're going to talk about functional programming a lot more in lesson 2 at the beginning of that lesson. But for now you can think of a more functional approach as being simply the ability to chain together method calls to have things execute one after the other. So now what we're doing is we're taking our collection of students and not using an explicit loop. Now we're passing the collection of students' records to a filter method. And the filter method is told how to do the filtering using a predicate interface. The predicate interface has a single method, and we use an anonymous inner class to define what that method is going to do. So in this case it's a method called op, takes a student as a parameter, returns Boolean. We compare the graduation year of our student to 2011. The output of the filter method will be a subset of the students that we have to start with, which will only be the students who graduated in the year 2011. We take that subset of data and we pass it to another method, in this case called map, which uses another anonymous inner class called mapper to determine how to actually do that mapping. And in this case, it has a single method called extract, takes a student S as a parameter and returns a double. For this, we take the collection of students who graduated in 2011 and we convert that into a collection of records of the scores of those students. So at the end of the map, we have all of the scores that the students who graduated in 2011 got. We pass that collection of data into what is in effect a reduce operation, but it's a special form of reduce, which is max. So it takes all these double values and looks at them and determines which is the highest value. And we return that result as our end result. So this is good. So this is much better in terms of looking at how we can do parallel processing, how we can use those multi-core, multi-CPU machines. We don't have explicit iteration. There's no loop there. So the iteration can be handled internally within the filter or the map or the max method. That means that if the library code wants to do that in parallel, we haven't forced, by defining the filter and the map methods, we haven't forced an order of execution on that. So now we're not doing it inherently serially. We can do it in parallel if we want to. We can also apply some other optimizations so that if we wanted to, we could do lazy evaluation, we could merge together the filtering and the mapping, so we did them as a combined operation on each element as it comes through the set of method calls. Because we don't have a variable which we're updating explicitly here, we're also thread safe. So the client logic, what we're looking at here, is stateless. The result is generated internally, so we don't have to worry about the state being modified within our code. That's great. What's the downside? Well, the downside is very simple. It's just plain ugly. And what I've done to kind of illustrate that is I've put some of the code in red and most of the code in black. The code that's in red is actually what we're really interested in. We've got a collection of students, we're after the highest score, we want to filter, we want to test against the graduation year being 2011, we want to map, we want to get the score, we want to max. All the rest of it, the fact that we're using a predicate of type student, which has a method called op, returning a boolean and so on, is boilerplate code. And we just really don't want to have that. And that is what Lambda expressions are all about. It's how we can simplify this kind of code in order to make it easier to understand. If we rewrite the code that we had using Lambda expressions, we can see suddenly that it becomes much simpler. So now what we're doing is we're saying, in the case of the filter, we need to define this single method called op that we have in our predicate. And you can think of a Lambda expression at this point in time as being like a method, but it's not really a method, and I'll explain that as we go through other parts of the lesson. But for now, think of it being like a method. It's like the method that we saw in the anonymous inner class in the previous slide. For filter, we have a method whose parameters, in this case, is student S. That's the left-hand side of the arrow. The body of the method is to return whether the graduation year is 2011 or not. And immediately you can see that this is not like a method as we're used to, because there's no explicit return statement. So the compiler will infer from the fact that we're comparing graduation year to 2011 that the result is going to be a boolean. Similarly, when we look at the map method, we're passing in a Lambda expression. The left-hand side of the arrow is the parameters, student S. The right-hand side is the body, which simply returns the score of that student, and the compiler will infer that that's double based on the fact that the signature of getScore is to return a double. Max doesn't require a Lambda expression, so it just returns the maximum value. This gives us something which is now much more readable. So it's more abstract in terms of the approach that we take. And because it's much simpler in terms of the code, there's much less code that we have to look at, it's much less error prone. We don't have to worry about, do we get the type of the method right? Do we get the type of the generic parameter right? All of those things are done for us by the compiler. So we have a much simpler way of looking at code when we want to do this kind of thing. To summarize section 1 of this lesson then, we needed changes to the Java language, not just to the APIs, so that we could simplify how we could deal with parallel coding. What Lambda expressions really gives us is a very simple way now to be able to pass behavior as a parameter to a method. And we've had that in the past in terms of anonymous inner classes, but because of this rather verbose syntax, it's always been very difficult to use that effectively. So now we have a simple way to pass behavior as a parameter as well as values, because most of the time we pass values as parameters. Now we can pass behavior as well. And we can also assign behavior to a variable if we want to. And that is the end of part 1 of this lesson.